Hello viewers, here is Dr. Mala Das Sharma. Welcome you to my tiny YouTube channel MALACHEMPHILIC. Today I am going to start video number 122 and this video is the episode number 62 of Chemical Thermodynamics, where the topic is material equilibrium for closed thermodynamic system. So let's start. So the condition for material equilibrium including both phase equilibrium and reaction equilibrium. Now here I am considering a closed system which is in mechanical equilibrium and thermal equilibrium. That means pressure is not changing with time and temperature does not change with time. See, here one thing I want to tell you, this equilibrium means, this equilibrium means, say for example, you have taken a gas, this is my system, enclosed in a cylinder which is attached with a movable piston. Now at this condition, that means in the stationary condition, this is pressure of the gas is equal to pressure of the atmospheric pressure and piston pressure, whatever it is. Now, say it is in mechanical equilibrium means the pressure will be same every point. Now suppose if you push this piston, that means compression. If the compression occurs by pushing this piston, then what will happen? Now the pressure will increase. But equilibrium, mechanical equilibrium will reach means pressure, that increased pressure will be same at all the points. Okay, that is mechanical equilibrium. So now our system is a closed system which is thermal and mechanical equilibrium, and one more condition I am putting, it is held at, now I am keeping temperature and pressure constant and it proceeds towards material equilibrium. Then how it is possible? It is a closed system. For open system, matter can be exchanged with the surrounding, but closed system, how it is proceeding to material equilibrium? Yes, here we can consider the irreversible chemical reaction, the chemical reaction which is occurring irreversible. So with time product concentration will increase, and when the reaction will over, generally 100% reactant will not convert to product. So at the end product concentration will be more maximum and the leftover reaction concentration also will be there, and that concentration will not change with time. Okay, then it is in equilibrium. And the interface transport of matter, that means we are considering a closed system but it's a heterogeneous, number of phases are there. So the matter can be transported from one phase to other. Okay. Then under this condition that irreversible chemical reaction may occur or interface transport of matter occurs in the closed system at constant temperature and pressure, and when this thing occurs, these are all this spontaneous process, then we know that for irreversible reaction or spontaneous transfer of matter, this Gibbs free energy G will decrease. Okay, and at equilibrium G will reach to the minimum value. So that is only written here. Considering a closed system in mechanical and thermal equilibrium and held at constant temperature and pressure as it proceeds to material equilibrium. We know that during an irreversible chemical reaction and interface transport of matter in a closed system at constant temperature and pressure, the Gibbs function G decreases. So dG less than 0 as it is going, means occurring. Okay, and at equilibrium G reaches to minimum. Now, see, in my last video, I have derived this key equation for thermodynamics that you have seen, that was dG, and if it is a multi-phase system, considering for all the phases, dG is equal to, we know, VdP, here it is for all the phases, minus again for all the phases, S means entropy, VdP minus SdT, plus this summation of alpha for all phases for I for all component. I maybe 1 to say n or 1 to j, whatever it is, mu I alpha dni alpha. This I derived for the open system, where I told open system can exchange matter with the surrounding. Now my system is closed, no doubt, but already I have explained that transfer of matter from one phase to another takes place, or irreversible chemical reaction or whatever it is. Now if I consider this overall change in the Gibbs free energy, that means change of Gibbs free energy of all the phases, this I am taking it as overall dg, and this is equal to this I am taking it as overall vdp, overall change of this change for all the phases, then minus s dt, then plus summation of alpha, summation of I, then mu I alpha dni alpha, right? Now, at constant temperature and pressure, so we can write at constant temperature and pressure, what we can write? dt is equal to 0, then dp is equal to 0, and at equilibrium, when the equilibrium is reached, then at equilibrium our dg will be minimum is equal to 0. Then what we can write from this equation? I can write 0 is equal to 0 minus 0, then plus summation of alpha, summation of I, mu I alpha phase, I have taken summation dni alpha. Okay. Now from here, what can I write? I can write it as summation of alpha, summation of I, mu I alpha, dni alpha, that is equal to 0. Okay. So, this is the equation for what? This is the equation for material equilibrium, So material transport was there. Now it has reached to the equilibrium. Material equilibrium, and what is the other condition? Closed system, and what is the other condition? Constant temperature and pressure, and of course PV work only. When you have derived the parent equation, we are considering only pressure volume work, PV work only. Okay, so this is the equation for material equilibrium, when the material equilibrium is reached for closed system under this condition, constant temperature and pressure, and of course PV work only, right? Now, if I consider the material equilibrium in a closed system held at, say I am writing material equilibrium in a closed system held at constant temperature and volume. That means we have to consider the Helmholtz free energy function. You know Helmholtz free energy function, that is at constant temperature and volume. In that case, then what I should write? I have to write dA. If I write alpha phase, that means then I have to take the summation. This is equal to minus S dt. So this is for alpha phase, and then minus PdV, alpha phase, then plus same thing, summation of alpha, summation of I, then mu I alpha, dni alpha. Right? Now this overall, this work function change for all the phases. This summation of d alpha I am writing is dA, and overall this things is say minus s dt, then this is minus p dv. This overall I am writing it as p dv, then plus summation of alpha, summation of I, then mu I alpha, then dni alpha. Okay. Now, at constant temperature and volume, say at constant temperature and volume, what can I write? I can write this dt is equal to 0 because I have taken that condition, constant temperature, volume and closed system, and your dv is equal to 0. Then when the equilibrium is reached, that means at equilibrium, when the equilibrium is already reached, then dA also is equal to 0. Then once again it is what it will be, dA is equal to 0 minus 0 plus summation of alpha, summation of I, then mu I alpha, dni alpha. So from here what can I write? From this I can write same thing, that is summation of alpha, summation of I, then mu I alpha, dni alpha is equal to 0. Okay. So this I have derived for what? Material equilibrium. Material equilibrium, number one condition. Then closed system, second condition. Then constant temperature and pressure, temperature and volume, and finally PV, pressure volume work only. Okay. Now I have derived this equation under this condition, material equilibrium, closed system and constant temperature and volume PV1. For this material equilibrium, I have derived this equation, and you see this equation is exactly same as that of earlier one, where that was the material equilibrium, closed system, but constant temperature and pressure, and other thing PV work only. Okay. So not only the material equilibrium condition valid for equilibrium reached under condition of constant temperature and pressure and temperature and volume, that we have already shown it. Under these two conditions, material equilibrium means equation for material equilibrium is same. But it holds no matter how the closed system reaches equilibrium. Whatever way it reaches equilibrium, this equation for the closed system, this material equilibrium equation is same. Okay. Now we consider, say for 1 minute, say for, I am writing this infinitesimal reversible process in a closed system, where this PV work only, means already this is always true, closed system and PV, pressure volume work only. Then that equation we know that dg is equal to vdp minus sdt. Okay. Say I am taking, this is my equation number, say 1. Right. Now, just now I have derived this equation, which is the for this equation, which is the key equation for thermodynamic system. That was dg is equal to vdp minus sdt plus summation of alpha summation of I mu I alpha dni alpha. This is the key equation, and here it is at, what are the condition? I put the condition, it is for closed system, right? Closed system, and then I put the condition PV work only at constant temperature and pressure, whatever it is. So this is my equation number 2. Now, if I make equation 2 minus equation 1, then what will be left over? dg cancel, vdp all cancel, then my equation will come same. Summation of alpha, summation of I, then mu I alpha, dni alpha is equal to 0. So, this is my equation number 3. Right. So, this is for what? This is for reversible process. Already I have written reversible process, closed system. So, this one is the equation for material equilibrium. Material equilibrium under what condition? Closed system, okay, and of course PV work, right? So, this equation always holds good, right? So, therefore, see, if the system reaches material equilibrium under condition of constant temperature and pressure, then G is minimized at equilibrium. We have seen dG will be equal to 0. If the equilibrium is reached under condition of constant temperature and volume, A is, that is, work function is minimized at equilibrium. But if the equilibrium is reached under other condition, okay, the other condition means not at constant temperature, pressure or temperature volume, then neither A nor G necessarily minimized. But in all the cases, whatever way the equilibrium is reached, in case of material equilibrium, in all the cases, this equation, summation of alpha, summation of I, mu I alpha, dni alpha, this is equal to 0. That was my equation number 3. So, this is equal to 0 in all the cases. Okay, already we have seen this material equilibrium equation is same for under constant temperature pressure or constant temperature volume. But not only these two, whatever way equilibrium is reached, for material equilibrium, this is the general equation. So, therefore, this equation is the desired general condition for material equilibrium. When the material equilibrium is reached, then this condition will be fulfilled. Hope you have understood. Thank you.